Hi guys, thanks for coming tonight. We are going to be talking about SQL Server and Pure Storage and talking about how SQL Server can leverage the benefits of a solid state array and in particular some of the advantages that Pure Storage offers. Before we get started, a little bit about me. I am a husband of a magnificent woman and a proud father of 5. Thankfully, she allows me to be here to do this kind of stuff. Right now, she's at home alone, hopefully not being beat up by the 5 children. I'm Indy Pass Vice President, so the local SQL Server user group. I have been on the board of the local user group for 4 years now, and I've been the food guy for 6 years. So I hold the highest position of food guy and likely will retain that position for a very long time. I've been working with SQL Server for a very long time, since 1997, as both a developer and an administrator. I am a Microsoft Certified Master for SQL Server 2008 and a Certified Solutions Master for the data platform for SQL Server. And if you can ask any of my coworkers or anybody who heard me talk before, I am a database automation enthusiast and some might say evangelist. So one of the things we're going to be talking about today is how we can use Pure Storage to make our life better. Little mini agenda. So I don't like to do anything without doing some education first. So today we're going to be talking a little bit about why SQL Server cares about I/O, what that means to SQL Server. And then we will go over, and I have some baseline OLTP workloads running, and we'll see how the Pure Storage compares to a classic spinning disk array. So let's get started. SQL Server storage is based on a hierarchy. This hierarchy starts with what you guys know as the file. Almost everyone who's worked with SQL Server knows that there's a file or files on the system. People refer to these as the MDF, or the data file, or LDF, the log file. Inside that file is not just a bunch of random stuff. So if you ever opened up one of those files, it may look like a bunch of random hex value code. It's actually not random at all. Within the file, there is an extent. So there is a logical construct on top, inside of the file that says every 64 pages is an extent. So what's a page? A page is an 8 kilobyte data element within the file. Everything in SQL Server is stored on a page. So if you can think about data for SQL Server, we have the file, we have a bunch of pages called extents, we have the page, and then we have the row. So if you're used to working in SQL Server and you get rows back, those rows exist on a page, which is part of an extent, which is part of a file. One thing I like to tell people about SQL Server data storage is that we have the 8 kilobyte pages. There's 1 to n rows per page. All structured data is stored in one of 2 ways. Either it's random in a heap. So if you create a table and do nothing else and put data in it, it is almost random where in that file that data may reside. There is some order to it based upon what free pages are available, but you cannot expect there to be any physical order to the data. The other option is the clustered index. With the clustered index, whatever you define as your clustering key, that's how the data will be stored on the page, and that's how the pages will be referenced. So by adding a clustered index to the table, you can guarantee the order that the data will reside within the file. Unstructured data is still stored in 8 kilobyte pages. So you think of you have structured data, which are your data rows, right? Those are your rows and columns. Unstructured data is stuff like images or large text or XML blobs, that big stuff that really is not row data, it's unstructured. So if any of you guys in here are using SharePoint, hopefully that when you think about where you store those files, those are stored in the database unless you're using some alternate method. Those are stored in groups of 8 kilobyte pages. My favorite analogy when I'm talking about storage in SQL Server is the phone book. Unfortunately, phone books are really hard to come by around here, so we don't have one to show you. But within the phone book, if you can imagine, you have pages of people's names, and how are they organized? Last name, that's right. So when we have a phone book organized by last name, that's our clustering key. So if you can just imagine that within this phone book, that's our database file. And you open it up, every page on the phone book is an 8 kilobyte page. You can fit so much data so many people's names will fit on that 8 kilobyte page. The unstructured data in this example are the ads. So if you think about opening a phone book, you may have ads spread out sporadically. Those still have to fit on that page, that 8 kilobyte page in that phone book, but they can be all sorts of unstructured data, but they have nothing to do with the rows that may exist with it. They can be related to it, but the data itself is not row-based. So when you think about how SQL Server stores data, think about the phone book. Every page within that phone book has names on it. The clustering key, if you have a clustered index, is going to be last name in a phone book. Does that make sense? Awesome. RAM. So how many of you guys, when you think about sizing a SQL Server, think, I want the most CPU and the most RAM I can get, right? How many of you guys know why? Okay, this is a quick primer on why RAM is so important. All the things, and I did that on purpose, my kids love saying all the things, must pass through RAM. So nothing in SQL Server comes directly from disk. Now, there are some things that go directly to disk, so backups will sometimes bypass the buffer pool, but there's a special chunk of RAM that's reserved specifically for backups. So when you think about SQL Server, everything has to go through RAM. If there's not enough RAM for your entire database to fit, or for all the database that SQL Server needs to run the queries, it starts paging out to disk files, or pages it doesn't need anymore. It uses basically least recently used algorithm, LRU algorithm, which says that if this hasn't been used for a while and it wasn't used very much, get rid of that first. However, if I need to replace all the data pages, SQL Server will replace all the data pages. So that's where having a fast disk comes into play. If you don't have a memory resident workload, then you need I/O speed to keep up with your queries. When we think about how SQL Server uses disk, so we've talked about how SQL Server stores data. We've talked about why SQL Server needs disk and what it does with it and why RAM is so important. Let's talk about how it uses disk. SQL Server has really two basic I/O footprints. We have random reads, which means that it's going anywhere, right? So if you think about a random read in that phone book, if I tell you to go find all the Neiers in a phone book, what do? You flip through it and you're like, Neier, right there. You don't have to look through every page. You aren't reading the book. You're finding Neier immediately because you know your alphabet, I hope you do, and you're able to find the N's and the NE and then the NEI and so on and so on. That's a random read. So if you can just think of SQL Server going and finding little bits of data here, and little bits of data here, and little bits of data here. That's a random read. A sequential read takes that phone book, and if I ask you to find me all of the Kyles in a phone book, what would you have to do? You have to start at the beginning, open the book, and page by page, read every page to find me all the Kyles. That's the same way a sequential read works. It starts at the beginning and pushes all the way through until it gets to the end of what it wants to get. So it's a very large singular read. So it reads a whole bunch of data at once. Random reads are going all over the disk. Sequential reads are going to a similar spot on the disk and going and grabbing the data. Random reads are going all over the place. Random reads and writes are 8K to 256K chunks. So if you think about data size, you have your phones are probably, what, 8 gigabytes for phones, 16 gigabytes for phones. SQL Server deals with 8 kilobytes. So gigabytes, megabytes, kilobytes. 8 kilobytes to 256 kilobytes chunks. So when it goes out to get a random read, it's either 8 or 256 or in between. It goes, grabs little chunks. Sequential reads are 8 to 256 kilobytes, same as the random reads and writes. However, if you have Enterprise Edition, it can grab 1 megabyte chunks. So if it's doing read ahead and it says, hey, I can take advantage because I know where these files are, it will actually read 1 megabyte chunks and get that data into SQL Server quicker by reading larger chunks at a time. And then sequential writes are almost always 8 kilobytes in size to 60 kilobytes being the log file. It actually flushes out the log file in those writes of 60 kilobytes. So if we're talking about I/O, SQL Server has come a long way in trying to help us to make our I/O faster. And I call these the I/O compensators. So if you think about all of the improvements that have been made in SQL Server over the past 10 years, a lot of them have to do with trying to figure out how to squeeze more I/O out of a system that's not keeping up with all the other aspects of the system. So if you think about a computer, and you think about how much faster the CPUs have gotten over the last 10 years, how much more RAM you can fit into a computer over the last 10 years, the disk that sits there, by comparison, is slower than tape was 10 years ago. So if you think about backup tapes 10 years ago, disk, by comparison to the horsepower that we have in the server, is the same as tape was back then. So I/O isn't keeping up. Excuse me. But SQL Server has been compensating, right? The guys up in Redmond are pretty smart guys, and they keep giving us stuff like indexes. Indexes have been around forever. Whether it be physical I/O on the disk or logical I/O in memory, they still compensate for I/O speed. So we have indexes. We have compression. Compression's awesome. I've seen anywhere from 2 to 1 to 10 or 15 to 1 compression ratios in SQL Server databases. It depends on what's in it. And the great thing about SQL Server compression is it stores it compressed on disk, which means it now has to make fewer I/Os to get the same data, and it leaves it compressed in memory. So now I can fit more of my database in memory, reducing the I/O I have to do, and the I/O that I do have to perform is less. So compression is a significant I/O compensator. Partitioning. One thing that's little asterisk here, that's enterprise only. Partitioning, enterprise only. You're going to see a theme here on this slide and the next slide. Indexes is the only one that we have that's standard edition. Partitioning. Partitioning allows me to take a table and work on sections of it at a time, or to run queries on sections of it at a time. The idea here is that I can load the most recent partition, and I don't have to worry with all the data that may exist in all the other partitions. I can query specific partitions, and all that other data doesn't have to come up from disk. It never has to touch RAM because I don't care about it, because I'm only caring about the partitions. In this case, I can say I only care about 2005 data right here. SQL Server never loads these tables into RAM. It only loads the 2005 data. So it's compensating for I/O by bringing up less data. Now, some really cool stuff. Column store indexes. So column store indexes, if you're familiar with the VertiPack engine or the tabular data model, so if you're thinking about VertiPack or you're thinking about Power Pivot and Excel, all of them use a similar technology here in SQL Server database engines called column store indexes, where it stores the data in a columnar fashion. So remember how I said, if you think about a phone book, that all the names are in there and those are rows? If you can just think about, instead of storing Neier Kyle and Neier James and Neier John, instead of storing those names independently, it stores Neier and says what all columns it points to. So it's reducing the storage, so it's essentially a compression, and it allows for significantly faster aggregate queries. Because if I want to see all the values for column A and they're all together on a data page, I don't have to go touch 20 data pages. I can touch one, and it knows how to build the aggregate immediately. So column store indexes are an I/O compensator. In-memory OLTP. So this one is more of a logical I/O compensator, but it is new to SQL Server 2014. It's called Hekaton is the code name, but it's actually in-memory OLTP. And it takes an OLTP workload that would be normally memory resident and makes it even faster. So as we're moving from the different compensators, we've had indexes for a long time, then we had partitioning and compression, and then we had column store indexes, and now we have Hekaton. So these advances in SQL Server have been to make SQL Server use less I/O, whether it be logical, in memory, or disk, so as it's pulling the data up from disk. So one of the things that we could use to judge the performance of a system is the TPCC Benchmark. This is an older benchmark. There's a newer one that we have, but I'm not using that one because I don't have that one available to me. So the TPCC Benchmark is an OLTP workload, and it represents a heavy write, low read ratio. And if you were looking, you're seeing on each side of me these little pictures as red, green, and blue, and they're bouncing up and down. Well, the reason I had these here is they're very important. So over here, we have a pure storage array. This one has the exact same workload running as this one over here. This one here is 28 spinning disks. One thing I'd like to show you here is the red, that is our latency. That is the average seconds per transfer. So when you think about how long that I/O takes to go all the way up and down, so you have SQL Server request the I/O and it has to go all the way down the I/O, come all the way back up. That red is how long that's taking. And when we look at this, on the 28 spinning disks, we're in the 10 to 20 millisecond range for this workload. The pure array is 1 or less. So when you think about needing random reads, latency is king. So if you've got a highly random workload, which is generally what an OLTP workload is, you want low latency. And that's what Pure is providing. So let me show you something here. Let me escape out of this and bring this up. So I'm using a program called HammerDB. It's a free program. And it's just running a TPCC benchmark and running 20 concurrent users against each of the databases. So it's just a TPCC. I did a 64 warehouse build of the database, and it's running 20 users. So it's apples to apples on both sides. So that's going to remain running. But one of the advantages I like to tell people about Pure is I don't have to think anymore about where I put stuff. So if you think about one of the things that we have to do as DBAs when we think about performance is where am I going to put my data files? I need multiple data files. I need to partition. Excuse me. I need to partition. I need to worry about keeping stuff in different places. That's no longer a need with an all flash-based array for performance. Now, you could still argue logical needs to do that, and there may be in-memory needs that make that better. So you may still get performance benefit out of partitioning, even though your I/O subsystem is screaming fast, because SQL Server may have to get less I/O because you've partitioned it out. So some of the I/O compensators don't go away, but you aren't doing them to compensate for disk I/O. You're doing them to compensate for other bottlenecks. So it's allowing you to do your job a little differently. I don't have to think about tiering. So I don't have to think about, okay, I need to make sure this stuff's on RAID 10, this stuff's on RAID 5. I don't really have enough storage, so maybe I think about like RAID 6, or my backups are on SATA and my database is on 15K SAS. I don't have to think about that because I just put everything on there. And it's all fast and I don't think about it. So in this query window, I've got a database group called Pure Demo, and it's talking to both these servers. So I have liquid and solid. Solid is the pure array, and liquid is the 28 spinning disks. And so what's going to happen while I have my workload running if I try to go run a CheckDB? You'll notice what happens here on the pure side is that my latency stays low and my bandwidth goes through the roof. So that green line is how many bytes per second I'm moving, or how many transfers per second I'm moving through. So I'm transferring over here nearly 8,000 IOPS. Over here, I'm getting 2,000 with right now it's looking at a 400 millisecond latency. Over here, I have not gotten to 5 yet. So I'm running an OLTP workload simultaneously on the same database that I'm running an integrity check. That integrity check is running, causing me to need more data, creating more IOPS. But when you look at the two systems, the Pure is keeping up. The 28 spinning disks isn't. So I don't have to be as picky about when I do my maintenance. So there's still some logical blocking that occur. So you have to think about that from a logical perspective and from a user application perspective, but not from a disk performance perspective. It removes a variable from what you have to think about. So that's a check DB. And I will say, how many of you guys are doing regular check DBs? If you're not, you should. Many other smarter people than me have explained why, so I won't go into it today. But if you're not doing regular integrity checks, you need to figure out how to get that done. And if you're doing it for performance, you can see the guys here to talk about pure arrays. The other thing I want to show you here is a backup. So here is my TPCC database, and I can't do it yet because I'm still running over here. So backups are incredibly I/O intensive. So when you think about a backup and what it has to do, it has to take all the data pages that are in the database and move them from the data file to another file. So if you're using backup compression, if you're using SQL compression, both of those help that performance bottleneck, but it's still a lot of I/O. In this environment, all my stuff's on C on both boxes because I want to do an apples-to-apples comparison. Both virtual machines have the same affinity. Both virtual machines are the exact same configuration. I'm going to stop this. I'm going to run the backup. Notice when I stopped that, this came down. That one over there was done running. This one over here was still running. Same size database. Now let's back it up. I'm backing up to the same drive that I'm reading from. I'm also running a full OLTP workload while I'm taking the backup on the same drive that I'm working from. I want to point out again, the pure array has gone up to 2, but it's hovering an average of 1 millisecond. This one over here got up to 30 or 40, and now it's back down to 20, and the backups are still running. So when you think about what you want to do in your environment, you can think about how the pure array can simplify your management as well as make things faster. So it's not always about speed. Sometimes it's about cost savings for how much work I as a DBA have to do. So if you want to think about what you can do as a DBA to make your life simpler, which I'm always trying to figure out how to make my life simpler, not having to think about your storage is one way that you can do that. Any questions? So data in action, pure storage, and SQL Server works great. Thank you guys, and if there's no questions, then we will get on out of here. Thank you guys.